Deep in the cosmos, when a massive star exhausts its fuel, it concludes its life in a cataclysmic supernova explosion. What remains is a dense, city-sized corpse. This is a neutron star. Packing the mass of a sun into a sphere only 20 kilometers across, its gravity and magnetic fields reach extreme limits. These remnants, known as pulsars, serve as the ultimate clocks of our galaxy, spinning with incredible precision. Deep in the stellar graveyard, pulsars act as cosmic lighthouses. As these ultra-dense neutron stars rotate at incredible speeds, they emit powerful beams of radiation from their magnetic poles. As the star spins, these beams sweep across the cosmos like a rotating beacon. When a beam crosses Earth's line of sight, we detect a rhythmic, precise pulse, marking time with unmatched accuracy. This emission is not just a simple flash, it is a manifestation of extreme physics. From material accretion to high-energy polar eruptions, pulsars stand as some of the most energetic phenomena in our galaxy. Imagine packing the entire mass of 1.4 suns into a sphere just 20 kilometers across. The result is a structure so dense that it defies ordinary physics. This is neutron degenerate matter. To visualize this, a single teaspoon of this material would weigh billions of tons, crushed by gravity into the ultimate state of matter. Why do pulsars spin so incredibly fast? Think of a figure skater. When they pull their arms in during a spin, they rotate much faster. A star acts just like the skater. As a massive core collapses from millions of kilometers across to just 20 kilometers wide, it shrinks its moment of inertia. To conserve its angular momentum, the spin speed must skyrocket. Pulsars are defined by their extreme conditions. They possess magnetic fields trillions of times stronger than those found on Earth. These immense magnetic fields act as a cosmic engine. They whip charged particles into motion, accelerating them to velocities near the speed of light. As these particles travel along the magnetic field lines, they generate the powerful radiation beams that we observe as periodic pulses across the universe. Without these extreme magnetic fields, the pulsar would remain silent and dark. They are truly the foundation of a pulsar's existence. By measuring the rhythm of their rotations, we find that millisecond pulsars maintain timing stability that rivals or exceeds our best man-made atomic clocks. These stars act as cosmic lighthouses. Their rotation is so consistent that the drift is less than 1 second every 10 billion years. This incredible precision makes them vital tools for mapping the galaxy and navigating the depths of space. At the heart of the vibrant Crab Nebula lies one of the most famous objects in the sky, the Crab Pulsar. Born from a supernova, this classic pulsar provides a unique window into the energy dynamics of young, rapidly rotating stars. It acts as a high-energy cosmic laboratory, helping astronomers study the intense physics that follows a star's final collapse. By observing this pulsar, we gain vital insights into how these extreme objects lose energy and influence their surroundings. Deep within our galaxy exists a cosmic giant known as PSR J0740+6620. Weighing in at over 2 solar masses, this pulsar is one of the most massive neutron stars ever discovered. By comparing it to other compact objects, we see that J0740+6620 sits right at the upper edge of what a neutron star can physically become before collapsing. This graph illustrates the mass-radius relationship. PSR J0740+6620 helps astronomers determine the Tolman-Oppenheimer-Volkoff limit, the critical threshold where a star must finally collapse into a black hole. By studying such a massive object, we gain insights into the fundamental nature of dense matter and the fate of stars. Some pulsars are not just solitary beacons. PSR J719-1438 hosts a truly exotic companion that defies imagination. This pulsar is orbited by a collapsed star remnant, a carbon dwarf that has essentially crystallized into a giant, diamond-like planet. This discovery proves that pulsars can harbor solar systems far stranger than our own, with matter compressed to densities that create literal cosmic jewels. It is a perfect reminder that the universe, in its extreme density, crafts objects that push the boundaries of planetary science. Scientists have recently achieved a monumental breakthrough by using pulsar timing arrays. By observing a network of stable, rapidly rotating pulsars across our galaxy, astronomers can monitor their pulses with extreme precision. These pulsars act as cosmic clocks, ticking at perfectly predictable intervals. However, when gravitational waves from distant, massive binary black hole systems wash over our galaxy, they warp the fabric of space-time. These massive ripples cause the pulsar signals to arrive at Earth just a fraction of a second earlier or later than expected. By tracking these subtle timing residuals across many pulsars, researchers have confirmed the existence of a stochastic gravitational wave background. This breakthrough marks a new era in astronomy, allowing us to listen to the low-frequency vibrations of the universe, shaped by the most massive objects in existence. The holy grail of modern astrophysics is to find a pulsar orbiting a black hole. This pairing would be the ultimate laboratory to test Albert Einstein's general relativity. A black hole creates an extreme gravitational well. By tracking a pulsar as it orbits, we could map space-time geometry in regions where gravity reaches its absolute limit. Finding this pulsar black hole pair would allow us to observe how gravity warps space-time. It would be our best chance to see if Einstein's laws hold up under the most crushing gravity known to science. The quest continues. Just one discovery of such a system would be enough to confirm or challenge our fundamental understanding of how the universe functions. Traditionally, pulsars were identified by their steady, rhythmic radio signals. However, recent scientific advancements have revealed that many pulsars are virtually silent in the radio spectrum, yet highly active in higher energy bands. Using the electromagnetic spectrum as a guide, we see that radio waves are just one small part of the story. Radio-quiet pulsars focus their rotational energy into X-ray and gamma-ray emissions instead. Analysis from observatories like the SKA and VLA show distinct temporal profiles. These light curves highlight how some pulsars peak in X-ray energy, despite having no detectable radio signature, challenging our historical models of stellar energy loss. By studying these radio-quiet pulsars, astronomers are rewriting the rules of stellar evolution, proving that the universe is far more diverse than our first radio telescopes ever suggested. For decades, our view of pulsars was limited to what our eyes could see through telescopes. But in the modern era of astronomy, we have moved from simply looking at the universe to listening to its symphony. By combining radio, gamma-ray, and X-ray observations, we map the full energetic landscape of these cosmic clocks. But the greatest breakthrough is the ability to detect gravitational waves. Interferometers like Virgo allow us to hear the ripples in space-time generated by extreme events. Combining these data allows us to paint vivid 3D pictures of neutron star mergers and binary systems, revealing the secrets of the most extreme events in our galaxy. Astronomy is no longer a single sense. It is a multi-messenger discipline, transforming how we understand the fabric of the cosmos. Our galaxy is teeming with secrets. Astronomers estimate there are over 100,000 active pulsars hidden throughout the Milky Way. However, we have only cataloged about 3,500. This massive gap highlights how much of the cosmos is still waiting for us to uncover its pulse. Each undiscovered pulsar is a potential cosmic laboratory waiting to be found. Pulsars have evolved from astronomical curiosities to primary scientific instruments. They allow us to probe the very fabric of space-time. By observing how their signals travel through the cosmos, we can map the curvature of space-time. They act like beacons that reveal the gravitational influence of distant galaxies and black holes. In binary systems, pulsars provide unprecedented data on gravitational waves. Their extreme stability serves as a testing ground for general relativity itself. Pulsars are no longer just passive objects in the sky. They are active instruments driving our understanding of the universe. Pulsars act as nature's most accurate clocks. We use their precise pulses to test the limits of Albert Einstein's general relativity. By monitoring these pulses, we look for tiny timing deviations that shouldn't exist in our current understanding of gravity. General relativity describes space-time as a smooth grid. But but it doesn't account for quantum effects at the smallest, densest scales of the universe. Finding a deviation could reveal quantum gravity, the missing key to how the entire universe functions. Deep in the constellation of Pictor, we find PSR J0437-4715. It is the brightest millisecond pulsar in the entire sky. Because of its incredible stability, it acts as a celestial anchor. Scientists use this pulsar as a benchmark to calibrate the timing of pulsar arrays across the galaxy. As the pulsar rotates, its magnetic beams sweep through space with perfect precision. It is the gold standard for our timing experiments, allowing us to map the universe with extreme accuracy. Massive stars live dynamic lives, burning through their nuclear fuel until they reach their final, inevitable end. When gravity wins, the core collapses into a neutron star, birthing a pulsar with intense magnetic fields and rapid rotation. The resulting pulsar is so dense that it exists in a state of matter physically impossible to recreate within any laboratory on Earth. These objects mark the transition from standard matter to the most extreme, dense states of existence in our universe. The next decade of pulsar research is set to transform these spinning corpses into our most precise scientific instruments. With massive next-generation telescopes like the Square Kilometre Array, we are drastically expanding our catalog of observed pulsars. These precise timings allow us to map the gravitational wave background, revealing the distant, violent collisions of supermassive black holes. This research promises to reshape our understanding of gravity, extreme magnetism, and the mysterious birth of black holes. Pulsars are much more than just the corpses of massive stars. They are nature's most extreme laboratories. They allow us to probe the absolute limits of physical reality, challenging our understanding of gravity, matter, and the fabric of space-time itself. By observing their incredibly stable, rhythmic pulses, we are mapping the structure of our galaxy, one beacon at a time. Pulsars hold the keys to the future of astrophysics. They show us that even in the quiet of space, the secrets of the universe remain, locked in their eternal, rapid rotation.